Hello, so today I'd like to solve the problem z to the n equals z plus 1 to the n, where z is a complex number. And the first thing that I'd like to point out is just that there are only n minus 1 solutions to this problem, because if we raise this right side z plus 1 to the n, use the binomial theorem, the very first term is going to become z to the n plus a whole bunch of other stuff depending on what n is, and then the z to the n's are going to cancel each other out, so then we're going to just be left with n minus 1 solutions. So that's the first thing. The next part is the fact that we can divide both sides by z plus 1 to the n. So we're going to say that z over z plus 1 to the n is 1. And we can look at this and realize, well, z over z plus 1 equals 1 is the one of the roots of unity. So because of that, we can use de Moivre's principle. I don't know if it's principle, but de Moivre's formula. And what we are basically going to do is say, well, that means z over z plus 1 is r, which is 1, so 1 times the cosine of 2 pi k on n plus I sine of 2 pi k on n. Let's just put that where that's really 1 to the nth. But 1 to the nth we know is 1, and then we know we don't need that 1 anymore. So what we have is z over z plus 1 equals this de Moivre's formula. So we can now move the z plus 1 to the right and rewrite this 2 pi k on n plus I sine 2 pi k on n. And then if we take the time and realize, well, z can be broken up into its real and imaginary components, we'll be able to have this equation in two parts, a real part and an imaginary part, and then we might be able to solve from there. So I'm going to write out z in their real and imaginary parts. So we're going to say let z equal x plus iy. So x plus iy is x plus 1, because that's the real part of that number z. X plus 1 plus iy times the cosine of 2 pi k on n plus I sine of 2 pi k on n. Okay, now we are going to distribute this right side out, and I'm going to kind of do it in two parts. I'm going to focus on the real part, and then I'm going to focus on the imaginary part. Obviously, you could do it any way you want and then reorganize, but I'm going to try to save a little bit of room. So x plus iy is my left side. X plus 1 times this is the part of my real solution, x plus 1 cosine of 2 pi k on n. And the other part of my real solution is going to be my iy times I sine 2 pi k on n. And we know I times I is -1, so this is going to become negative 1 y sine 2 pi k on n. And now we're going to deal with the imaginary parts. So the first part of my imaginary is going to be iy times that. So I'm going to have plus I, and I'm going to put it in brackets, so I'm paying attention. Y cosine 2 pi k on n. That's one of the parts. The other imaginary part is going to be x plus 1 times this sine of 2 pi k on n. So plus x plus 1 sine 2 pi k on n, and I just squeezed it in. Okay, so we have our real and imaginary parts. So we're going to break this up into two different problems now. We're gonna solve the real part and solve the imaginary part separately. So I'm gonna put the imaginary part over here. We're gonna work on that over here. So we have I, y is, and it's this whole thing, I times y cosine of 2 pi k on n plus x plus 1 sine 2 pi k on n. That's my imaginary part, and I'm going to do my real part over here, just so we can keep it separate. So we have the real part is going to be x equals x plus 1 cosine of 2 pi k on n, and minus y sine of 2 pi k on n. So the nice thing here is we have two equations and two unknowns. Our unknowns are x and y, x being the real part of our solution, y being the imaginary part of our complex solutions, pluralize it. And because we have two equations and two unknowns, maybe we'll be able to solve for this. So I'm going to work on the imaginary side. The first thing I notice is I can cancel out my i's by dividing both sides by I. And so I have y equals this. Then I'm going to move my y's together so I can solve this equation for y. So I'm going to cancel out my i's, and then I'm going to subtract y cosine 2 pi k over n from both sides. So y minus y cosine 2 pi k on n is the same as x plus 1 sine of 2 pi k on n. Now I can factor out a y from my left side, and I'm going to get y equals, not equals, y times 1 minus cosine of 2 pi k on n, and that is the same as x plus 1 sine 2 pi k on n. And now I can divide both sides by 1 minus cosine. So y is x plus 1 sine 2 pi k on n over 1 minus cosine 2 pi k on n. So I just solved my imaginary portion of my equation for y, and I'm going to take this and I'm going to plug it in for my y over there. So we'll have x is x plus 1 cosine of 2 pi k on n minus this whole thing, x plus 1 sine 2 pi k on n over 1 minus 2 pi k on n. I'm sorry, 1 minus cosine of 2 pi k on n times my initial, that's sine of 2 pi k on n. So now the goal is to simplify this equation and see if we're able to actually solve for x, right? This whole equation, it has the k's and the n's, but those just represent particular solutions for particular problems depending on what we initially choose n for, and then k tells us which solution we would be finding. So I'm going to attempt to solve this problem for x at this point. I'm going to do two things at once here. I'm going to factor out an x plus 1, and I'm going to multiply these two signs together. So we now have x is x plus 1 times this cosine of 2 pi k on n minus this x plus 1 is part of this now, sine squared of 2 pi k on n over 1 minus cosine of 2 pi k on n. So then we look at that, and hopefully you can remember some of your trig identities and realize that sine squared is just 1 minus cosine squared. So we'll rewrite that. X equals x plus 1 cosine 2 pi k on n minus 1 minus cosine squared of 2 pi k on n over 1 minus cosine 2 pi k on n. And then we should be able to look at this numerator, 1 minus cosine squared, and realize, oh, that's just a difference of 2 squares. So we then do this. I'm just copying again. 2 pi k on n minus 1 minus cosine 2 pi k on n, 1 plus cosine 2 pi k on n over 1 minus cosine 2 pi k on n. So by realizing that we can multiply the signs together, we get sine squared. That turns into 1 minus cosine squared. 1 minus cosine squared is just 1 minus cosine times 1 plus cosine. Now we're able to just cancel these out, which turns out to be really, really nice. So we are going to cancel these out. Now we're going to distribute this negative sign over this and copy this again. X is x plus 1 times cosine of 2 pi k on n, and then we're distributing this negative sign here, minus 1 minus cosine of 2 pi k on n, and this whole thing is being multiplied by that. Now we should be able to look at that and go, oh, we have that and that, right? We got a positive 1 and a negative 1, they cancel each other out, so we now have x plus 1 times negative 1. So x is negative 1 times x plus 1 is negative x minus 1. We add x to both sides, we get 2x is negative 1. X is negative 1/2. What this tells us, if we think about our real and our imaginary plane, our complex plane, we now know that all the solutions to this problem, all n minus 1 solutions to this problem, lie on the line negative 1/2, on the real line of negative 1/2. So that's kind of neat. We have this whole plane, and now we know all the answers lie along that dotted line I drew there. So we now need to plug back in to figure out what the y values are for this same thing. So we come over here and we look. The only place to plug in negative 1/2 is here. Negative 1/2 plus 1 is positive 1/2. So now we know that all the imaginary proportions of our complex solutions are going to be 1/2 sine of 2 pi k on n over 1 minus cosine of 2 pi k on n. So we now know, remember that we let z equal x plus iy. So now we know that the answers are always going to be z equals negative 1/2 plus I times this. So I'm just going to write that down as our last idea. Z equals negative 1/2 plus I times 1/2 sine 2 pi k on n over 1 minus cosine 2 pi k on n. And there we have it. Those are all of our solutions. I'm going to give you an example of how we could use this to find it, find the actual numbers. Here's my eraser. So I'm going to get rid of most of this work here, and this is our big conclusion. So I'll get rid of this here. let's do something easy and say we were trying to find the solutions to z cubed equals z plus 1 cubed. Well, first of all, there's only two solutions to this problem. The first solution is going to be where I'm going to write it this way, z where k equals 1. Our first solution where k equals 1 is going to be this answer here, -1/2 I, plus I times 1/2 sine of 2 pi, k is 1, over n is 3, over 1 minus cosine of 2 pi times 1 over 3 as well. And we can actually simplify this thing right here and realize that that's just -1/2 plus I times the sine of 2 pi over 3 is 4 pi over 6, 1, 2, 3, 4 pi over 6. I believe that is -√3 over 2. And then the cosine of that is, positive √3 over 2. And then the cosine of that is going to be -1/2. So that's the same as -1/2 plus I √3 over 4 over 3 over 2, which is, oh my goodness, my √3. Give me 1 second. Pardon me. √3 over 6. Oh, -1/2 plus I √3 over 6. Yeah. So if we cube that, we should get itself, which is kind of cool. And we could find z of k equals 2 in a similar way. -1/2 plus I times 1/2 sine of 2 pi times 2 over 3 over 1 minus cosine of 2 pi times 2 over 3. And so that would give us our other solution to this problem. Okay, I want to conclude with a couple more quick ideas. This was like a long way to do this problem. And when I initially saw this problem, well, I thought to myself, we're taking this line, like I think about it in the polar form, and we're taking the length of this line and we're raising them both to the nth power. So that means the length of each of these lines has to be the same. So that means their modulus has to be the same. So I'm going to erase this over here and just show it a much quicker way we could have come up with the real portion of the solution, because we now know that the modulus of z has to be the same as the modulus of z plus 1. It seemed like it was just a logical idea to me that the lengths had to be the same. Well, we can rewrite this as x squared plus y squared. Remember that we said z equals x plus iy. So then we can also do the square root of that. We can do the same thing over here and say this is x plus 1. That's our real part plus our y squared. So we have that. Taking the square root of both sides of an equation, well, we can just square both sides of the equation and get rid of it. So now we have x squared plus y squared equals, I'm going to multiply my x plus 1 squared out and get x squared plus 2x plus 1 plus y squared. And now I'm going to look and go, oh, I can cancel out an x squared, I can cancel out a y squared, and I get 0 is 2x plus 1. I should be able to solve for x really easily. I'm going to subtract 1 from both sides. Divide both sides by 2. and I get -1/2 equals x, and we just figured out that the real part, just like we did before, is along the vertical line of the real part of the complex plane, x equals -1/2. And so that's about that. Attached to this video, I also created a Desmos file where you can choose n to be any number you want, and you will see the k-1 points plotted on the complex plane. And all I did was just plot this point using Desmos. I just think it's kind of a neat visualization of what we just proved. Thank you. Enjoy your summer.